Yes, we can. So,
Okay.
okay, the
Right.
stage is yours.
So, right. Thank you. So we are beginning with design of acoustically IMAV motors. This is the paper number 9. Like Jose said, we're a little bit not on schedule. So if we can do this more efficiently, that will be great. So design of acoustic still map motors, please. Continue with Gojan, Jardin, and Mosheta, please.
Hello, can you hear me?
Yes, we can.
Okay, nice. Well, hello everybody. My name is Pietro Livolzi and I'm a PhD student at ISAE Supero working for Parrot Drones. And today I'm going to present to you our work on the design of acoustically stealth MAV rotors. So first of all, I go through for the context. So as you may know, quadcopter drone design is challenging from different reasons. Because of their dimensions, in fact, and their weight, the Reynolds number that is encountered is lower than the 10 to the power of 6. This, in fact, will limit the flight endurance. On the other hand, since quadcopter drones are destined to be more and more employed for delivery of goods, their acceptance due to their emitted noise is a concern for the public. On the other side, for military drones, they must be acoustically stealthy to accomplish reconnaissance missions. Here you can see the characteristics of a professional MAV drone, on which we have a low Reynolds number, a low Mach number, incompressible flow then, and a weight that is lower than 1 kilo. For these reasons, the objectives of our paper are to improve the flight endurance and reduce the emitted noise by changing the rotor geometry. So in the past, multi-objectives optimizations of propeller have been studied. Here I show the results from Pagano et al. On a P180 aircraft propeller in a pusher configuration. Here you can see the aircraft. In this case, the objectives were to the aerodynamic efficiency in cruise conditions and the tonal noise at takeoff. Here you can see on the right-hand side a graph on which on the x-axis you have the dB decibel at takeoff, the tonal noise takeoff, and on the y-axis the eta cruise, the efficiency in cruise condition. So the best geometry would have been here on the upper left part of the graph. As you can see, the optimized result, there is not one optimized results, but there are different optimized results that belong to the Pareto front that is showed here. However, this optimization is very different from the one that we will present here, because the Reynolds number is very high, higher than 10 to the power of 6, and the Mach number is higher as well. And also the fact that here they studied a propeller in a pusher configuration, while we will study a propeller in hovering conditions. So the starting geometry of our study is the NACA 12 rotor that has been experimentally studied by Gojon et al. And is showed here in the right image. The parameters of the rotor are the rotor is composed of 2 blades. It has a NACA 12 constant airfoil throughout the span of the blade, a diameter of 10 inches. It has a pitch of 10 degrees and it is untwisted. So in order to simulate the aerodynamic efficiency of the rotor, we used a steady nonlinear vortex lattice method that has been developed by Zhou et al. This one works by assuming that the flow is incompressible, inviscid, and irrotational. These 3 assumptions lead to the Laplace equation that allow us to calculate the airfoil properties everywhere near the rotor. So in order to run the NVLM simulation, we need 3 inputs. the geometry, the rotational speed of the rotor, but also a lookup table. The lookup table is needed to take into account the viscous effects due to the low Reynolds number encountered by the rotor. In order to create those lookup tables, we run X-foil simulations. Here you can see an example of lookup table for an AK-12 airfoil. We have, in fact, the lift and drag coefficients as functions of the angle of attack and for 3 different Reynolds number. And the outputs of our NDLM simulations are the thrust, the torque, but also the figure of merit that corresponds to the aerodynamic efficiency of the rotor. The experimentally measured sound pressure level of the AK-12 geometry, initial geometry, is shown here on the right-hand side. Here you can clearly distinguish a set of discrete peaks that compose the so-called tonal noise and a highly frequency broadband noise. For our study, we will calculate the first peak of the tonal noise, also called first BPF SPL, by means of Farasat formulation 1A equations in order to calculate the tonal noise. Our tonal noise, however, is composed of 2 components, the thickness noise and the steady loading noise, since we run steady aerodynamic simulations. Since both aerodynamic and acoustic softwares are coding through Python, we chose PyMO as the optimization framework and the genetic algorithm NSGA2 as since we wanted to run multi-objective optimizations and we wanted to get the Pareto front. On this optimization, we activated the crossover and deactivated the mutations. For our optimizations, we run 40 generations, with each one of them having 100 candidates. On the right-hand side, you can see the design variables that have been chosen, as well as the lower and upper bounds. As you can see, the twist, the chord, the skew and rake have been modified. And on the center GIF, you can see how the geometry is built. As said before, the 2 objectives for our optimization are the endurance on one side, that is that we want to maximize through the rotor figure of merit. And on the other hand, we want to minimize the first BPL, blade passing frequency, SPL, for a microphone located at a far field distance of 1.62 meters and an angle of 30 degrees below the rotors. The only constraint set for our optimization is the thrust, for which we have a rotor thrust of 2 newtons that corresponds to 800 grams of the full drawn weight. To ensure the 2 Newton thrust, we need 2 different calculations, and we will assume that the thrust follows a quadratic curve. Here you can see the results of our optimization, and on the right-hand side you can see the figure of merit and the first BPF SPL, the noise, as function of the generation. You can see that the moving average has converged after 30 generations on both curves. On the left-hand side, you can see the first BPF as function of the figure of merit. Here you can see the initial geometry in the blue dot. The ideal candidate would have been on the bottom right part of the image. However, we cannot see only one optimized result, but we can see another Pareto front. This time, this Pareto front is different from the other one that we saw before, since we can clearly distinguish 2 different Pareto lines. We can also see the green dots are the last generation candidates, and they are almost all are very close to the Pareto front. As you can see, since all the Pareto front is on the right side of the initial geometry, we can clearly see that all the Pareto front has a higher endurance. Most part of the Pareto front is below the initial geometry. That means that their emitted noise has been improved. So from this Pareto front, we chose two different geometries. One that is marked in green and is located here as the highest figure of merit. That means the highest endurance. By 50%, the figure of merit is higher than the initial geometry. The brown dot corresponds to the lowest SPL candidate with an SPL less than 30 dB to respect to the initial geometry. On the right-hand side, you can see the difference between both candidates, on which we can see that the highest figure of merit candidate has a small core tip, and it is pointing backward, while the lowest SPL candidate has a bigger chord at the tip, and its tip is pointing forward. However, we can clearly see that both geometries have a tip that is pointing downward. To understand the overall shape of the Pareto front, we searched for the parameters that led to these results. And in fact, two parameters came out. First of all, the rotor solidity. Here you can see the candidates colored by their rotor solidity that is defined here. And we can see that there is a brutal change in the rotor solidity at the intersection of the two Pareto lines here. In fact, candidates with lower acoustic footprint have higher solidity. A positive skew angle, we can see that it further improves the figure of merit, of course, to the detriment of the acoustic footprint. Since in the literature there are no optimizations that include both rake and skew distributions in quadcopter rotors, we run a total of 4 different optimizations, and the Pareto front are here showed. The orange optimization does not include the rake and skew distribution in the design variables. Once we allowed the optimization algorithm to change the skew distribution, the red Pareto front, we can see that the figure of merit is slightly improved. The green Pareto front, on which we allowed the rake distribution instead of the skew one to be changed, we can clearly see that both figure of merit and SPL emitted noise are slightly improved. At the end, when we allowed the algorithm to change both rake and skew distributions, we can clearly see that both figure of merit and SPL are improved, and the Pareto front is a different shape with the two Pareto lines. So if we sum up, we saw that to increase the endurance of MAV rotors, we should reduce the chord length at the tip, and we should sweep the blades backwards. On the other hand, to reduce the tonal noise of MAV rotors, we should increase the rotor solidity by increasing the chord at the tip, and we should sweep the blade forward. On both cases, we should have a pointing downward tip. So we, in the future, we will run unsteady and VLM simulations for the best candidates in order to take into account the unsteady loading noise. We will also take into account manufacturing and the structural constraints, such as the weight, the structural solidity and stuff, to then 3D print the optimized rotors and evaluate them at ISAE supero anechoic chamber that is displayed here. And at the end, we will add the broadband noise into the optimization loop to take into account the full acoustic spectrum. So thank you for your attention, and do not hesitate to contact me at the following address. And if you have any question, don't hesitate. Thank you.
Thank you very much, Pietro. Are there any questions from the audience? While we wait for other questions, I actually have a question for you. In terms of the balance in which you are trying to minimize the sound that is being produced by the rotor versus the mobility of the actual MAV, are there any things that you need to balance there? I mean, have you seen any position in which you need to reduce the sound that it produces, but by doing so, maybe the handling of the MAV is being impacted by that?
Well, of course, it will be impacted by the rotor, but in our case, we only studied the rotor, the sound emitted by the rotor, and the figure of merit in the overing configurations. So we did not run the simulations on forward flight or different configurations.
Right, but that will be, I think, very interesting, because something tells me that will be something of a balance act that you'll need to obtain to actually, produce a stealth MAV, but that is also very, very mobile.
Yeah.
Right. So I'm not seeing any other questions from the audience, and considering that we needed to start a little bit late in your case, I'm going to call on the next paper so that we are able to to get on schedule. But thank you very much, Pietro. That was very, very interesting. Especially since I do a little bit of audio as well. I think we're a little bit of a distant cousins in this regard. Okay, so next paper is a click mechanism moderates drones flapping wing kinematics for enhanced thrust generation. That's paper 20. I would like paper 20 to start its their presentation, please. Okay.
Okay. Hi everyone.
Good.
I'm Wu Shangling from National Jiao Tong University in Taiwan. And today I'll present about a click mechanism moderate drones flapping wing kinematics for enhanced thrust generation. And my supervisor is Professor Liu Yiqiang. This is outline of my talk. First, I'll introduce about click mechanism in different insect and pest works. Then I'll show our design of click mechanism and ornithopter prototype. Next, I'll talk about wings kinematics with and without click mechanism. And last is conclusion and future works. Diparent insect like flies can fly for long endurance. In extreme condition, a hungry fruit fly can fly for 1.75 kilometer and 2.35 hours. They benefit from low mass and disk loading and an elastic mechanism, which is the click mechanism we'll mention later. And we are wondering that if the elastic mechanism remain applicable on larger flapping drone. So click mechanism is part of the flight mechanism in diparent insect. Diparents such as flies has indirect flight muscle, which do not directly attach to wings, but pull the back of thorax closer to the belly. The configuration of the thorax is like a lid, a pot, and the wing as a spoon. When press the lid, the spoon will rise. And in this case, tertium, the dorsal side of the thorax, is like the lid, and pleural, the ventral side of thorax, is like the pot wall. The deformation and relative displacement of turbulent and plural pull the wings to flap. Unlike other mechanisms, a click mechanism has two stable positions, uppermost and the lowermost. Force is required to switch from one stable position to another. And this by stability is a result of the toggling of V-shape joint. There are two links between turgid and plural. The two links form either V shape or lambda shape. The total length of two links are greater than the distance between the turgid and plural. And Brennan simplified the click mechanism into geometric model and assumed that the force is applied to the joint rather than the back of thorax. Then he calculated vertical reaction force. On middle joint as this plot. Where two links move toward middle point, the edge of turgid and plural bend like spring and push the two links away from middle point. After the links pass the middle point, they'll rapidly jump to the other stable position. Thus, this is called bistable click mechanism. To verify whether click mechanisms effect in flapping wings mechanism, Dr. Qin Yaowei designed a mechanical prototype to compare the thrust generated with or without click mechanism. These prototypes have wingspan of 130 millimeters. It turned out that click mechanism almost double both the thrust and the thrust to power ratio. However, the previous 3-gram prototype of click mechanism does not produce enough thrust to carry batteries. And so we wonder that can we use a bigger motor to drive a larger wing on a click mechanism? And will the larger click mechanism bring the same benefit as it did to the smaller flights? So with the help of click mechanism and a 5.6 grams motor, a wing pair of 340 millimeter span and a 2.2 gram can now fly a 37.4 gram ornithopter forward for 15 minutes. And now we would like to share how it works. So this is the ornithopter we finally made. It has wingspan of 34 centimeter and weighted 37.4 grams. And in this research, motor acts as the flight muscles and linkages are spring act as a thorax mechanism. This slow motion videos shows the linkage system when motor runs. Then we put the wings on, and this video shows the wings flapping. We observe spring effect on wing kinematics. We use the model of Bernard and Chen and design a model which turbines are fixed and pull the middle joint of links. The motor drives the cranks through the gear set, and rotating cranks then drive the wings to flap back and forth through a crank rocker linkage system and a double rocker linkage system. All linkages mechanisms and cantilever spring are made of POM board. And for referenced non-spring mechanism, the cantilever spring in red circle are replaced by a regular joint. And this slide shows how spring of click mechanism works. When links pull by the gray driving link, the cantilever spring then bend outward. After the links go through midpoint, the cantilever spring push links to jump toward the lower stable position. And as shown in the video, it will jump to the other position. Then we fix the click mechanism to a tensor tester to do a vertical stretching test. The vertical force curve is like the Thurman result early shown in Brennan's geometric model. But in this result, it's asymmetric. Then we simplified our click mechanism into geometric model and get the relations between input and output angles. Then we plot the free body diagram. Neglect the mess of links. We can get relation between vertical force and links positions by two torque balance relation, which the torque to A and the torque to D. Moreover, we assume that when the spring fatigue, its balance position moves outward. So we added a bias angle when calculating spring force. And by this statics model, we plot the vertical force and compare with tensor test result. We can see that with 8 degrees of fatigue bias angle, the vertical force calculated are almost coincide with the experiment result. And finishing the driving mechanism and click mechanism design, we put the wings and assemble a complete click ornithopter. The wings are made of PU film with 30 micrometer thick and reinforced by carbon fiber rod, the black one. Each wing weighs 1.1 grams and span 140 millimeter. The whole ornithopter weight 37.4 grams, and the weight of batteries, circuit system, and tail weight over half of whole ornithopter. And the 340 mAh batteries can supply the motor to work in full throttle for about 10 minutes. We estimate the motor load from spring force, wind drag force, wind inertia, and motor inertia. We found that load from air resistance of wings are much higher than others. It shows that the wing flapping motion are mainly determined by motor. Linkages, the flapping motion are mainly determined by motor, linkage systems, and wing drag force. The spring of click mechanism only modulate the flapping speed curve to a small extent. Then we started to test the dynamic performance of the ornithopter with click mechanism. We took the tail off and do the takeoff test. This slow motion video shows how wings flapping. And in this video shows that it overcomes its own weight and take off, which means it generates at least 33 grams of thrust. We pull the tail back on and do a free flight test. The 37.4 gram ornithopter flies slowly forward with 80% of throttle. This flight can last more than 15 minutes, but not shown here due to the limited flight arena. And we fixed the ornithopter on the force sensor to measure the thrust generated during wings flapping. As in the video, the wings flap and generate a thrust upward. So we can measure the thrust by reading the mean vertical force on force sensor. And the result shows that the click mechanism improved the maximum thrust by 80% from 25 grams to 30 grams, while the power consumed are almost the same. Then we observe the wing kinematics. We overhead shoot the flapping motion with high-speed camera and measure the stroke angle and pitch angle of the wing face. We found that a spring in click mechanism postponed the flapping phase in this plot. Well, the flapping frequency of spring and non-spring are both 30 Hz. The spring decelerates the wind in former half stroke, then accelerate it later half stroke. Also, the spring slightly flattens the curve, which the root mean square speed of spring are lower than non-spring one. But the spring one generates higher maximum thrust. And we notice that the higher thrust is accompanied by the observed higher membrane tension and higher camber. And finally, we come to the conclusion. First, the click mechanism with a spring is a more powerful transmission as compared to the one without spring. The same flapping wings on the spring loaded mechanism are produced 80% higher thrust than the one on pure rigid mechanism, which is the revolute joint one. And the spring torque is only a small fraction of aerodynamic torque, but it moderates the flapping speed curve. And the spring postpones the flapping phase and also flattens the flapping speed. However, the spring effect on wing kinematics is not so much. And for future works, we wonder that the enhanced thrust with spring could be attributed to other factors like reduced friction, increased membrane tension, or wing camber. And we want to find a relation about this factor. And that is my report. Thank you.
Thank you, Shanling. Well, are there any questions from the audience? Okay. Well, while we wait for other questions, I have a question. You mentioned in the graph in which you were comparing the power consumption versus the thrust, exactly that, thank you. That although yes, at the 8-watt power mark, there is an 18% increase in thrust. There is a bit of a reduction close to the 2.1, 2.2 power or watt power mark. Is this significant, or is this something that you're also considering in fixing, or is this something that you can live with?
I think it's because in lower power, which means the lower flapping frequency, the aerodynamic force or the drag force does not do so many load for motor. So when flapping slowly, the spring of click mechanism do the main load compares to the aerodynamic force. So in lower flapping speed, the click one consume more power and generate lower thrust.
Lower thrust, right? Okay, yeah, that seems adequate. Or logical. Again, there aren't any questions in the audience, so I still have another one. So
okay.
Taking advantage of that, of this opportunity. although it's what I understood from your presentation, it appears that what you're trying to fix is, or the contribution here is, now you're using the click mechanism instead of another mechanism in terms of doing the flapping. However, I see that you require that these two motors should be in sync at all times so that there isn't any mobility from one side to the other. Do you have any mechanisms that force that that is the case, so that you don't have any that issue?
So sorry, do it means that in two different prototype, the difference of two separate motor, or is this your?
Oh, right. Okay, now I understand. So basically, you have those two in using the same motor. Now I understand. Oh, okay. Right. Oh, so you only need one motor to do this flapping then. I'm guessing that's one of the contributions from your click mechanisms as well. Okay.
Oh, yeah,
rather...
that is two different prototype, but
okay.
Yeah.
Okay. Well, thank you very much, Wu Shanling. That will be all for you. Thank you very much for your presentation. Next up, we have propulsive efficiency of small multi-rotor propellers in fast-forward flight. That is paper 29. I'm guessing this is Liam Bullard, is it? Yes, Liam Bullard. So please come up.
Hey, good morning.
Morning.
I'll just get my presentation started.
Right.
One moment. Okay, so my name is Liam, and this will be a presentation about a fairly brief research project that was conducted at RMIT within the Unmanned Aerial Systems research team, and that is propulsive efficiency of small multi-rotor propellers in fast-forward flight. So first, the brief background of why these small multi-rotor propellers. In recent years, we've seen a pretty huge boom in small, mainly racing drone components. Includes a lot of propellers, a lot of motors, ESCs, etc. Compared to some of the things that we would have used for research in previous years, we suddenly have a huge abundance of parts. They are comparatively cheap, and there's a lot of variety. So sometimes there's some very unusual or quite otherwise difficult to get a hold of parts that are now readily available. So for certain MAV research projects, this presents itself extremely well. A pictured example, which is where some of the motivation for this project came from, is another Unmanned Aerial Systems team project that's, I think, made a few appearances in previous IMAV conferences, where we have 6 5-inch multi-rotor propellers where the diameter was a fixed constraint. And in this sort of regime, the only options available are these drone racing propellers. So they're really abundant, but there's not a huge amount known about them. The most common size that we see is 5 inches. That's the most common racing drone size. And they're obviously, as the name implies, racing drones, well and truly designed for speed, high power, and efficiency is effectively a byproduct. Now, in general, with MAV projects, we don't necessarily care too much about extreme speed, and efficiency is much more important. So to use that example of the Unmanned Aerial Systems wind measuring drone again, the flight plan of that aircraft is for a long continuous fast forward flight and then a fairly rapid return to the start so it can repeat that flight as many times as possible. Now, this requires, ideally, the highest efficiency that we can get in that forward flight mode to maximize data collection in a given sort of wind scenario. Now, with the propellers in that 5-inch range, there's very limited performance data available. So most manufacturer provided details are diameter and pitch. Some will provide a static thrust value. Some will provide slightly more than that. Generally, those values are slightly exaggerated and in some cases just outright false. So there's a significant need for some sort of experimental testing with some of these sort of racing components. Now, the manufacturers do generally provide us a geometric pitch for these racing drones. It typically ranges from 4 inches to 5 inches. You can get some slightly higher, some slightly lower, but the majority within this range. And what that really suggests with the sort of rule of thumb conventional propeller design is that the peak efficiency for these propellers will be in very high speed flight. So the question for this piece of research is basically, where does that peak occur and how fast do we need to fly to reach it? And whether the angle that the aircraft flies at really makes a significant difference. So to illustrate one of those points, the propeller in the image is sold as a 5-inch diameter and 5-inch geometric pitch, but compared to a series of other sort of 5-inch geometric pitch propellers that I had on hand, it actually has a significantly higher pitch. So even though this value is provided by manufacturers, it's not necessarily to be trusted. Now, the testing setup is quite simple. We have an off-the-shelf RC benchmark thrust test stand, which is able to measure both the thrust force and the mechanical torque generated by the motor. So we can test these propeller parameters independent of motor, speed controller, power supply, etc. This whole assembly was bolted to a huge stepper motor, which allowed for the entire assembly to be rotated. And all of that was controlled remotely through a computer and automated. So the whole flight testing process in the industrial wind tunnel resulted in around 250 individual propeller runs that were all automatically generated. Now, the propellers that were tested were all out of the HQ Prop sort of V series. So they're all 5-inch 3-blade propellers with pitch from 4.3, 4.8, and 5 inches. Now, these propellers were selected as they have a fairly reputable history. And in this particular series, conveniently, a very nominally identical blade profile for each prop, just with an increase in pitch for each one. The wind speeds that were tested and the flow angles were selected as being representative of the aircraft that these propellers were sort of selected for. So they were tested for a flow angle from 30 through to 50 in 5-degree increments, with the axial flow case left in as well for comparison. Wind speeds range from 10 to 20 meters a second, which was within the range that we expected this particular aircraft to fly. The power supply was used to simulate a 4-cell lithium battery. So the rotational speed of the motor varied somewhat, as some of the higher pitches could not achieve quite as high RPM as the low pitches, but it was approximately 30,000 for each one. Now, here we have a brief sort of subset of the results. And what we can see straight away is, for every case, the most efficient propeller that we have is the lowest pitch. To go along with that, each propeller observes its highest pitch at its lowest RPM. So what we're seeing there is the highest pitch being observed at the highest advance ratio. So the initial conclusion is that none of these propellers are realistically being flown fast enough in this test case to reach their sort of peak of efficiency. Everything that we're looking at is sort of past that point as it decreases. Now, within the individual propellers themselves, we can see generally that the lowest pitch is almost always the best performer, and the highest pitch is almost always the worst performer, which backs up that theory that the pitches for these propellers suggest sort of much higher forward speed. And interestingly, with the flight angle, we found that increasing the angle, so getting closer to an axial case, generally gave less efficiency. The angle seemed to have minimal impact from prop to prop. So if we increase the pitch angle of the aircraft, we don't suddenly see a higher pitch prop becoming more efficient than a lower pitch prop. So this was just a very, very brief data set. We'd like to expand it with a fair few more propellers and slightly more sophisticated testing equipment, but it provides a sort of quick insight into some of what's available. And for these aircraft, that insight sort of shows where we should be aiming in terms of extending flight duration for this forward flight. And in some ways, why the cheap and abundant solution is not necessarily ideal. Okay. Thank you.
Yeah, thank you. Thank you for your concise presentation. Very to what my supervisor when I did my PhD said, very short and sweet, which is very good. My question here. While we wait for more questions from the audience, I have a question. So, you mentioned these 4 propellers that you are, or these 4 propellers that you tested. Have you seen any type of tendencies for the ones that are efficient and for the ones that aren't? Meaning, did you notice anything structurally that you say, oh, look, when they have this characteristic or this physical characteristic, they end up being more efficient or not?
Within this particular set of propellers, so all from the same manufacturer, there wasn't any particular or anything like that we really noticed. I did test quite a handful of other props as well that sort of didn't make it quite into the official data set. And there I found a lot flexed very significantly at high RPM. And if you looked at them sort of side on in the blade plane, you could see the tips bending really significantly forwards. Those ones suffered quite a lot. So at higher RPM, they had big efficiency decreases.
Right. So would that be something that you were, well, obviously right now you may not be willing because, I mean, you haven't, there isn't any concluding results here, but so would that be something that you would say to an audience member here that, well, if you see this bid on this type of propeller, try to avoid it? Could you could you be saying that, or do you need more concluding or experimental results to conclude?
We probably need to do a bit more experimental work, but I think it's been one of the big trade-offs with these drone propellers over the years is that we've moved from what was traditional RC aircraft propellers, which are normally like glass fiber reinforced nylon, to all of these propellers are polycarbonate.
Right.
They're a lot more durable and they don't shatter on impact, but they do suffer in terms of stiffness. And I think that's where we lose quite a bit of efficiency, especially at high RPM.
Well, that brings me to my other question, which is, were there any differences between the materials with which these propellers were built, or it seems at least the two that you mentioned in the images here, they seem to be based on plastic. Are they any other one? Are there any
Yep.
one of each one of them built in other materials as well, or were they only based on that material?
So these ones are polycarbonate as well.
Okay.
And the whole testing series was done with the same material.
Hmm.
It's, for the most part, the only material you can get these propellers in these days.
Right.
It's almost completely universal.
So there are any it's interesting because I would have thought that considering, oh no, carbon based or carbon fiber, I'm sorry, would have been something that, I mean, is that too brittle for because like you said, I haven't seen any other other type of any type of propeller, but I would have suspected that, I don't know, carbon fiber will be something that may be used, but is that too brittle? Is that too lightweight? Would it be less efficient than this?
Well, carbon is used quite often with larger propellers. It does work very well for those larger propellers.
Mm.
I think this is just an issue with the market itself, and that
Right.
these propellers are sort of $3 for a bag of 4, and
Right.
they are designed to be effectively disposable.
Right. Yeah, that makes sense. All right.
So for the drone racing side of things, it's fantastic. But from a purely functional point of view, they could be a lot stiffer.
Right. So basically, is that put this propeller on when you're testing the drone, so that if it breaks or jumps in or whatever, we can probably buy another one and replace it very easily.
Yeah, exactly. They're very, very replaceable.
Right. We seem to have a little bit of time here, so I'm gonna take advantage of, because I do have some question. I do have some other questions. You mentioned something in terms of the could you put the image in which you were presenting the test scenario in which you had the propeller and exactly, thank you. Here is something that I wondered. So I understand the 90-degree axial ideal, because that's where the wind tunnel is going, and you're basically trying to, well, achieve the movement of the rotor and etc. I also understand the hover one, which implies when the rotor is going this way and you have some winds that are on the other one. However, the 45-degree, in what circumstances do you believe that is going to happen? Because that seems like a really big pitch for a drone that has the rotors going that way, or in the hover side. I mean, that pitch is really aggressive. So, where do you see this happening?
So that aircraft that I mentioned at the start, I'll grab the image again.
Thank you.
This actually came from our flight testing.
Mm-hmm.
So that aircraft is flown directly into wind, and it does that at about 15 meters a second. And to achieve that 15 meters a second, it pitches to 43 degrees from memory.
Okay,
So
so
it's
you're testing this in
extremely aggressive. Yeah.
Right. So you're testing this also in a very windy and a very okay. Now I get it.
Yeah.
Right. Yeah. Because
So
my
that's
mind is in the race conditions, and it's like, wow, that's really that's just even going downward. But okay, so
it's very
here
extreme.
here comes the other question though. How are these propellers, the 5-inch ones that you tested, usually used for this types of maps?
They're not too far off it. So within the drone racing itself, there's probably not an average angle that extreme, but they certainly spend a lot of time accelerating at angles sort of 45 plus.
Right. Okay. Well, that's it for my questions. There isn't apparently any other questions from the audience, so I thank you very much, Liam. Thank you for the presentation. We're going to give a little bit of opportunity for the next presenter for aero-propulsive performance improvement of H2 powered UAS. I know we're a little bit ahead of schedule, but I think you can use this time to put up your presentation. I mean, configure anything that you need. That will be Nicola. Hello, Nicola.
Hey.
So in this way, I mean, your time is not still here. You have a couple of minutes. I think you still have a minute. So if you can take advantage of that and put your presentation up and configure your stuff,
Sure.
I'll tell you when you can. I'll tell you when you can start.
All right. Can you already see my screen?
I can see your screen. Yes.
Should be full screen now, right?
No, I am only seeing the PowerPoint presentation in terms of the actual PowerPoint software. I'm not seeing the full screen yet. Good thing we have a little bit of time here.
Okay, stopped it. And I'm going to restart. Okay. Yeah. And now?
There we go. Very good.
All right.
Right. Well, you're completely welcome to start. We're right on the mark of your start time, so you can start whenever you feel comfortable with. Thank you.
All right. So hello, everybody. My name is Nikola Gavrilovic, and I'm a postdoc at ISAE Aero from Toulouse, France. So I'm going to present you today the aero-propulsive performance improvement of hydrogen-powered unmanned system. So basically, this is a project which has an objective to design and develop an aircraft which is fully electrical and which is capable to cross the South Atlantic Ocean. So I'm going to go further. So the whole project has a historical context. It is inspired by the French company called Aero-propulsive. And this company in the beginning of the 20th century was transporting letters between Africa and South America. So you can see here an example between Dakar and Natal, Dakar in Senegal and Natal in Brazil. So it takes approximately 3,000 kilometers to do the journey. And you can see the pilot who was one of the biggest stars of the time, Jean Mermoz, who died in 1936. He disappeared in the sea. So the project is carrying the name of this pilot. So basically what you can see, if you want to stay with the first small study, if you want to stay with the design of the aircraft, which is powered by hydrogen, if you want to stay with a mass lower than 25 kilograms, you cannot do such a journey with classical batteries of lithium. Simply the energy density of lithium batteries don't allow you to do the journey. On the other hand, if you use one more extreme, if you use the liquid hydrogen, you can do much more than 3,000 kilometers. So now, if we compare here different sources of energy which can be used in this project, for example, as I told you, lithium polymer batteries. With that kind of energy, you can do approximately 400 kilometers. Now, if we pass to the technology of fuel cell and hydrogen, in the first case, I'm taking an example of 6-liter gas hydrogen with bottles which are compressed up to 300 bars. You are now more than doubling your energy density, and you can do around 1,200 kilometers for the same volume of 6-liter. But now liquid hydrogen, you can do much more. So you can do up to 4,000 kilometers. And of course, at the end, if you are taking the example of the thermal engine with 6 liters of petroleum, you can do even more. Of course, the quantity of the CO2 is in function, especially for hydrogen, of the production. So if the hydrogen is produced in a green way, from only the electricity which is produced in a green way, then we can have a completely zero CO2. just on the map, I was showing you what it represents actually in the world map range of 4,000 kilometers. So you can see that, for example, you can reach even the high northern parts of the planet if you start from Toulouse. So just to compare the two principal sources, you can see on the left a 6-liter gas hydrogen bottle. So usually they're under 300 bars, and the temperature is around 20 Celsius. And inside you have only 124 grams of hydrogen. When you take into account the efficiency of the fuel cell, you can calculate that you approximately have around 2,000 watt-hour. On the other hand, if we are talking about liquid hydrogen, we can take an example of almost the same bottle of 6 liters. Now you see that we are at a much lower pressure of only 2 bars, but at a temperature which is a minus 253 degrees. But I would like to point out that this is the temperature of the liquid hydrogen. And this is actually, you can look at this bottle as one big thermos. And actually the temperature of the wall of this reservoir is ambient temperature of 20 degrees. And in this kind of bottle, you have around 420 grams of hydrogen. So you can see that if you keep your hydrogen in a liquid state, you can have almost 3.4 times more hydrogen. But there is something that needs to be taken into account here, and this is a boil off. So your hydrogen is slightly heating, and you are releasing a certain quantity of hydrogen all the time. So this is something which has to be taken into account in the design phase, especially so that you are using all the hydrogen that you are actually boiling off. If you are using less than you boil off, you will lose your hydrogen in the free air. So basically, we have a partnership with a company called HES who supplied us with the fuel cell Aerostack 500. So this is a open cathode type of the fuel cell, meaning that this fuel cell is using the air from the ambient surrounding environment. And it has a maximal power rated at 500 watts. So we have, with our partner laboratory here in Toulouse, we have conducted some tests, performance tests and endurance tests. So you can see the graph where we have determined what is, for example, on the left, you have the fuel consumption in function of the load of the fuel cell and also the power of the fuel cell. So this is going to help, this is helping us actually in the design phase of the aircraft. You can see here some thermal images as well. So one of the main products of the fuel cell is the heat generated. So you can see here how the fuel cell is heating up depending on the power required from the fuel cell. So the project started with the designing of the aircraft. So it started with a preliminary design where different geometrical parameters and limits are determined. Those geometrical parameters and their ranges actually were used later for the genetic optimization in Python using a OpenMDAO package. And actually all the aerodynamical calculations were done with AVL, which has been modified to take into account the viscous effects. So there are some sub-programs within the optimization routine which calculate what is the mass of each configuration, what is the static stability margin. And all of this has been done with the principal constraint to be less than 25 kilograms and to be able to have a certain aerodynamic efficiency which is necessary to do the journey. So one of the results of this preliminary design is an aircraft with a total mass of 12.5 kilograms, which is flying around 23 meters per second, with a wingspan of 3.6 meters, and with a very optimistic estimation for the lift to drag ratio of 25. So you have the aspect ratio of 20 also. So basically it's a glider which is powered. It has to be a big glider which is powered. So for the technological innovations, we can imagine here a demonstrator, which is all of these dimensions that I previously told you, which is having a fuel cell, a liquid hydrogen tank. We are also having parts of the project which are developing controllers which are robust to the metric conditions. So we are looking what are the metric conditions along the journey. And we are having a global path planning along the journey. We had also projects which incorporate eco-design, meaning that all the materials that we plan to do and that we are using in the fabrication, we are thinking about the footprint that we are leaving. So it has elements of bioinspiration through some structures that has been studied in the project. Like you can see those fancy bio-inspired winglets inspired from the eagle wingtip feathers, but also some trajectory optimizations like energy harvesting. So like the albatrosses do, they exploit the wind gradient. So those kind of smart, intelligent ways of trajectory planning are also part of this project. And also in the end, it has one innovative try of using solar panels, but in this way, not only on the upper side of the wing, but also on the lower side of the wing. As we want to cross the ocean, so big surface of air, a big surface of water, we are testing some smaller aircraft to see if we can profit from a reflection of the water and how much, if we can actually detect something. So basically you can see here the detailed design of the aircraft. You can see that it's a very classical configuration. In front, what you can see is the system of air inlets, NACA inlets, which serve to inject air inside, which is used for the fuel cell, both to feed the fuel cell with oxygen and both to evacuate the heat which is generated by the fuel cell. Fuel cell you can see as a yellow box here. This is a configuration with liquid hydrogen reservoir. So you can see in the purple a small heat exchanger, which has actually the task to slightly heat up the very cold gas which is leaving the liquid hydrogen reservoir. So here you can see a first step of the fabrication. So it's a classical method of the fabrication of the aircraft with the frames which are cut with the laser machine or the plywood. Some of the plywoods have been reinforced additionally with the layer of the carbon. After that, you will see a bit advanced. This is another level of fabrication, which is wrapping the structure with the balsa wood, then layers of carbon, layers of glass, and in the end, like painting and varnishing the structure. So here is a preliminary, this is actually a final assembly. So what you see here are the holes which are missing to be filled with 3D printed inlets and outlets. And you can see also, I will talk a bit later about that the propeller has been integrated in the cone and what you actually get when you integrate the propeller in the cone. You can see here the final assembly with the disc, with the now glued positioned inlets, a certain configuration of NACA inlets and outlets with a complete wingspan of around 4 meters. So for some performance improvement studies, we also used in one of the projects some CFD studies. So you can see here boundary conditions, which are typical domain for half plane and inlet outlet symmetry and other boundary conditions. So what you can see here was the mesh convergence study. So ISIM was used to build this mesh, tetra mesh, and you can see that we've been trying to achieve a certain level of the Y plus on the walls. We have also looked into the convergence of the drag coefficient and lift coefficient to determine what is the necessary number of iterations for the steady simulations. And we have also looked what is the Y plus on the fuselage specifically and trying to resolve correctly the boundary layer on our airplane. So here we have also compared some results of the AVL with the CFD. So once again, I will just remind you that the AVL has been modified by Murat Bronz. I think he's currently present here in his PhD thesis, so that it takes into account a database of previously generated airfoils by X-foil. So it is taking into account the viscous effects for each section of the wing according to the Reynolds number of each section and lift coefficient of each section. So basically what you can see here is that we have quite an acceptable match between the two methods. And we have also continued to do further comparison between the two methods. For example, what you can see here is the trial to determine where is the neutral point of the aircraft. So this is just a variation of the pitching moment coefficient for a certain positions on the fuselage starting from the cone point. And we have also found less than 5% match of the position of the neutral point between the AVL and CFD. This kind of reassured us that the AVL is, I mean, considering the time it needs to run one calculation, quite powerful to do the even more complicated designs. So this is what I mentioned you before. Beside choosing the propeller, beside choosing the motor and variator, this was one special study which was actually trying to determine what would be the optimal position of the propeller in terms of starting position of the fuselage. So how much you should actually integrate the propeller in the fuselage. And why should you do that? Well, you probably know that almost first quarter of the propeller is not generating any positive effect. It is generating only the drag. So if you try to hide that out, you are going to save some drag. And in addition, you have a certain deviation of the flow because of your shape of the fuselage, which is also going to help you to have a slightly higher efficiency with already chosen optimal propeller. So what you can see here on the graphs is that you have two names. You have isolated. That means that there is no integration. So there is no effect of the flow on the propeller. So this is just if you take like a simple analysis of the propeller, like we are all used to do. While on the other hand, you have an example of an embedded propeller, depending in function of the propeller position from the cone tip of the aircraft. So what you can see is that actually, if you go on the left graph up to 50 millimeters from the cone tip, you're achieving higher efficiency with the propeller. So this helps us actually to choose where we should position our propeller on in the fuselage, and with that we gained almost 3% of the efficiency. This is at least what the theory was saying. Further analysis, you have here a comparison of the baseline study, which was received by the optimization that I showed you previously with the genetic algorithm, and the baseline V2 study, which was more easy to fabricate. So what you can see here, we have a slightly higher wingspan of the baseline V2 configuration. We actually want to do the flight test with that configuration, so we are actually also profiting with a slightly higher wing surface, so that we can achieve a lower speed of landing. So what you can see is actually that when you compare the viscous drag coefficient between the two, because you have a higher lift surface, you are having more viscous drag coefficient coming from your wing, and this is due to, as I explained to you, because you have more wetted surface, as you can see on the right. So we have also compared clean aircraft with bio winglet, with the simple blended winglet, and with the specially designed junction between the fuselage and the wing, so that we actually try to neglect all the small interactions like appearance of vortices in this region. So what you can see is that with the junction, you're expecting, at least with the CFD, a very small contribution of around 1% in the total drag, while with the bio winglet, you can go up to 5%, or blended winglet even more, a bit more. So 5% is typically something that you have on commercial aircraft as well. So we were quite okay with that result. I would like to tell you that recently we started, and very recently, I have also finished the wind tunnel campaign here in Super. So what you can see here is the low Reynolds number wind tunnel, which can go up to 25 meters per second with the speed. So we said that the three main objectives of these studies. So one was to determine the performance of the propulsive chain, so to test different propellers. The other was very important, to measure the mass flow in the fuselage. So on the right picture down, you can see a system of mass flow sensors, which are directly connected to the outlets of the fuselage. So basically, we are measuring, according to the speed of the wind tunnel and different parameters, what is exactly the mass flow inside the fuselage. And also the contribution to drag due to the NACA inlets, contribution to drag due to different structures like Karmans. This is our third objective. So we have 3D printed Karmans, and also modeled them from the special paste, which is called plastiline. You maybe know the kids play with that. So we also managed to measure the benefits with having a wing junction of around 3% of the total drag in the wind tunnel case. Here you can see the sensors for the mass flow in a more detailed way. So this is very important study, as I told you, because we need to make sure that the fuel cell is not going to overheat. So we need a sufficient amount of air going inside the fuselage. If the fuel cell is overheating, it will automatically shut down. And so far, up to these days, there is no way to automatically restart the fuel cell. There is just a simple button, which doesn't mean that it can be done, but for the moment it can be done. And on the other side, you can see a customly built control system for data acquisition, which is going to be later used for the flight test as well. So all the data in the wind tunnel were wirelessly transmitted through the XB on the computer, and we had all the sensors were connected to the card you see on the right. So these are some pictures in the end from the wind tunnel campaign. So you can see what comes maybe to your immediately to your attention are the NACA inlets in front and the outlets on the right. And thank you all for your attention. So if you have any questions, feel free.
Unfortunately, we don't have much time for questions. Your time is almost up. So right now I'm going to need to call it. Obviously, if some of audience members have questions, you're welcome to contact Nicola private in a private manner. But for now, I'm going to just need to say thank you. Thank you, Nicola, for your presentation.
No problem. Thank you.
No, thank you. So now we have a little. So now I'm going to need for the paper 11 implementation of copter propeller model to the problem of energy consumption minimization during lift phase to start preparing their presentation.
Yes,
I'm guessing is
Sergey
Serahvostov.
Yeah, I'm here.
Thank you. So, okay, yeah. I can see your presentation. I can see your presentation now.
Okay. Ladies and gentlemen, I am Sergey Serahvostov from Moscow Institute of Physics and Technology, and let me make my presentation concerning the implementation of copter propeller model to the problem of energy consumption minimization during the lift phase. So, what was the idea and the motivation? As we know, the main phase for the copter is hovering, but from time to time, at least from time to time, it must lift to some altitude, and maybe for some reasons this altitude must be rather high, and for this case we need to choose the flight mode to, for example, minimize the energy consumption. So the main thing is to minimize the energy consumption. And what are the steps? First of all, it was the less or more analytical investigation. So we need rather simple but very powerful formulas that help us to obtain the analytical results and use it and obtain real results for our investigation. As a traditional case, the propeller of copter, for example, can be described by so-called non-dimensional characteristics such as thrust coefficient, power coefficient, efficiency as a function of advanced ratio J. So as an example on this slide, you can see these characteristics for APC Sport 11/3 propeller. Some words must be given for the propellers. As we know, for hovering, the better the best choice is to use the propellers with a rather small pitch to diameter ratio, for example, such as pitch is equal 3 inches and diameter is 11 inches. So typical graphs are shown here, and for such a propellers there is no flow separation on the blades up to the 0 values of J. So let's discuss now about only this type of propellers. As we can see, for example, for thrust coefficient, the graph is practically the linear line from 0 CT up to 0 J. So one of the ideas is to approximate this graph by the linear function. And as for CP, okay, we think near the 0 values of J, it is practically constant. So the model of propeller proposed looks like like that. So CP is constant and CT is a linear function where J sub 0 is the point when the CT is equal to 0. So for thrust T and the power P, we have such formulas and coefficients that can be used in analytical investigation. Sorry. And if we resolve the thrust formula for frequency required, we obtain such an equation, and for our case, when the aircraft is hovering, or maybe lift with the constant velocity v, the thrust is given by this formula where m is total mass and n is the number of propellers. Also, interesting case is when the aircraft is hovering. If the copter is hovering, the formulas are very simple, and these simple formulas we can use a little later. So the main task is to minimize the energy consumption. So we must climb to some altitude h, and the energy consumption must be minimal. And so we can vary the velocity of lift, and substituting all these formulas to another formulas, you can see it in my article, we will obtain the result. Sorry. Okay, so time required, rotational frequency, and power required for lift with the minimum energy consumption is given at this slide. What is interesting? What is interesting, we have a rather simple, even not analytical, but practical way to obtain these values of, for example, rotational frequency and power. We just can measure these parameters during the hovering and then multiply them to these coefficients and obtain the parameters for the optimal lift. Also, what about the velocity of optimal lift? If we introduced the velocity of stream, of air stream past the propellers, and we can measure it rather simply, so the optimal velocity of climb is about this value of stream velocity past the propeller. So also we can obtain practically without any calculations this optimal velocity of climb by measuring the velocity of stream. And what about the maximum about the energy consumption? Optimal energy consumption is given by this formula within this model. So MGH is well known, and the efficiency of electrical part is also evident. And here is the maximal propeller efficiency corresponding to this model. But it's a very simple maybe formula, but it corresponds to the value of J, that is about a half of J sub 0. But in reality, this value of optimal J that corresponds to the maximal propeller efficiency is about 60 or 65% of J sub 0. So the next proposal is to make more precise model. Maybe for some cases the previous model is not good enough. So the idea is to approximate this CP by a parabola, where J sub 1 is the point where CP is equal to 0. So some formulas that are nearly the same that we obtained earlier. Also, the procedure of obtaining optimal frequency of rotation, optimal power is the same as for the previous case. Also, these formulas for optimal energy contains this part that is the maximum propeller efficiency for this model. So maybe one of the main conclusions is that the lift must be made at the mode of maximum propeller efficiency. But very interesting thing, as we know, the main mode of flight for the copter is hovering, and for the efficiency of hovering we have so-called figure of merit. And the idea is, okay, we need to make the more efficient lift, so we can use more efficient propeller, and we know that if we increase pitch to diameter ratio of propeller, the efficiency can be increased. But on the other hand, the figure of merit will decrease with the increase of pitch to diameter ratio. So this graph gives some information about it for this series of APC sport propellers, and we really see that the efficiency increases and the figure of merit decreases. So for every flight task we must choose some point that give us the total best efficiency, total best energy consumption. So we must take it in mind. And what about the comparison of our model with the reality? So there are three graphs that gives us the answer on this question. By red, there is theoretical lines, but according more precise model, second model. So we can see that the coincidence is very good. The accuracy is very, very good for my opinion, of course. So I think that this model can be used for the analytical investigation or maybe even can be used in numerical calculations somewhere. And another interesting question that can be analyzed: what is the maximal climb altitude for the copter if we use less or more this model? If we imagine that we can put different amount of accumulators and varying the accumulators, we can vary the maximum altitude. So the energy required for the lift to some altitude h can be given by some rather simple formula. And we see that in denominator we have this part that at some value of h is equal to 0. So it is evident that this condition, when this part is equal to 0, corresponds to the maximum of maximum available in very good conditions, maximum altitude. So parameter alpha is a power density of accumulator, and the formula is just this. So if we substitute the data for accumulators for efficiency of power plant, we can obtain about 30 kilometers. Okay, it's rather optimistic, but I think with some restrictions and more precise model, we can obtain about 10 or 15 kilometers. But as you know, the 15 kilometers is maybe the highest altitude for the commercial aircraft. So I think that theoretically, the good copter can lift up to the 10 or 15 kilometers. Why not? So here are some conclusions that can be made. Also, I want to say that more precise calculations and some interesting things you can use in my conference paper. So thank you for your attention. If you have a question, please ask me.
Thank you. I'm sorry. Thank you, Sergey. While we wait for questions from the audience, I found it interesting that, well, first of all, I think you completely verify this idea that while you have more efficiency, the merit, the figure of merit comes down. Which then is the balance here? I mean, what is the solution there? I mean, is there a solution that you could propose that says, you know, this is a very efficient and has an adequate figure of merit position in which you can recommend?
You see, it's like two parameters optimization. Yeah, just like Pareto optimal condition. And for example, you can have one task that you can climb on 10 meters and hover for 1 hour. Yeah, and another task is you must lift at 1 kilometers and hover about 1 minute here. You see, in this case, the results are different. Yeah. So I think it's just like some kind of two parameters curve. Yeah. Just like a Pareto optimum.
Right. So could it be possible, could it be feasible then to use a type of switch between different efficiency models depending on the circumstances, such as to say, well, we're still in this threshold of efficiency, but we're getting a figure of merit based on application per application? Then would that be then the answer to this?
I hope I understand your question. How to change this. The easiest way is to change the propeller from task to task. Yeah, yeah. So
it will be great that it will be great that we'll be able to change the propeller to change the propeller on the fly, right? Literally.
Or
right?
You can use the propeller with a changeable pitch. Yeah.
Okay.
But it needs some other devices. Yeah. So the reliability can be not so good as for simple propeller. Yeah. Also additional mass and some other problems. So it is a task for investigation.
Investigation. Very well. Very well. Right. I'm not seeing any other questions from the audience, so I'm gonna call it here and leave some time for the next presenter to configure and everything else. Thank you very much, Sergey.
Okay, thank you. Bye.
Right. So next up is 3D reconstruction based on NER single pixel for drone navigation under real conditions. Is the paper number 14. I see that there is our the person in the list of assistants, Carlos Osorio. I'm guessing is the name. So if you're able to start, putting up your presentation and configuring everything, so that you're able to start. Right. Right. So it's gonna be a video then. Okay. In this case, whenever.
Good morning. I share on presentation or video.
Phase 1, near single pixel for drone navigation on the riding condition by Quadcopter. Content of the section: I begin introduction, how does the riding lines performance of the vision system, single pixel application as a vision sensor, modeling near steam riding condition, 2D and 3D near speed, reconstruction on the right condition, evaluation of the projectile near speed as a new vision system for webbing, conclusion, and introduction. Currently, the vision sensors are too essential for application with webbing. For the way we can see different vision sensors for covering the spectrum electromagnetic from visible to microwave. Some applications need to have vision systems that are relevant with integration visible sensors with others as radar, thermal, infrared, and hyperspectral to compare the lemmings, other scenarios with scattering and low illumination. However, some of these vision sensors can be expensive or have high dimensions that can lack integration into gravity. Through the side water particles, the Reconstruction is based on the diameter of the water particle from the fall to the storms. During scattering for more notable for smart particles due to the space are more compact. The cross-section area of the pattern of light is a more significant increasing the attenuation. Extinction efficient on the right condition. When light interacts with a water particles, there are various physical phenomena occurring as reflection, refraction, absorption, and scattering. Effects that degrade the manufacture level of light due to decreased level photons depend by photodetector in the vision system. We can see an attenuation flux light reserved for the different writing conditions to extinction efficiency. This spectrum is high and decreased by the long wavelength. Change contrast on the writing. We can see the best performance in the right condition in the infrared vision system over the visible vision system. We can see the difference in the cluster of the infrared imaging compared to the visible imaging at the 1 meter. So a high value of the QS is a high attenuation. Of the laser server with that imaging will have a low contact. We increase the observation distance. It is possible can detect images in the visible while that infrared we can detect the objects due to the high performance of the infrared vision system on the other condition. We propose a vision system that works based on the single pixel principles to generate all the images. We can integrate into UES as an element vision. The near speed architecture proposed in this work is divided into two main parts. In the first stage, the elements used to generate imaging from the single picture principles. I have Inca photodetector and arrays of emitting near lens and ADC convector. The second step is the principle of electrical signal emitter by the ATV model. It digitalizes signal using IDC and the received data processing using and GPU unit. The GPU units using JSON Nano, the responsible for the generation, the Hammer pattern, and the processing the conversion data by ADC. The construction imagine usually draws the batch OMP algorithm running in the GPU unit. Imagine 2D based on to generate 3D imaging using J4J algorithm. For generation imaging, we have a less A2A array that the projection as surface environments type Hammer. We are captured by the photodetector that conversion the signal light and electrical signal, while the processing using and conversion sensing algorithm type batch OMP. By construction imaging using the measuring signal and the sequencer panel are. To the low solution imaging, we are planning a method super resolution based on C and M. This 2D imaging will be used to generate the 3D imaging. The modeling near speed fine condition. The final system will make a theoretical evaluation of the near speed on the right condition. To determine the range measure. The more considered some weather parameters in scattering, range speed, and model number of photons captured by the photodetector for different reflection index of the objects. They define the range measure of the different rollers from the 0.5 millimeter distance to 3 millimeter heavy range. The effective range measure from 17 to 33 centimeters. The range measuring, we can see that the number of the photon degrades in relation to a distance. We can see the constant degrade from the high constant to low constant in relation to a distance. For evaluation of the vision system and near speed, we view at the test space with emission in the right area from the 14 to 30 to 33 centimeters to simulate the right condition and a change in the background illumination near to a scenario outdoor. This test base allows us to see the effects of the light in the infrared spectrum and evaluate the reconstruction. We can see 2D near speed imaging using different scanning methods. Here is zigzag and spiral. In different sequence, the projection Hammer patterns. For generation 2D imaging, we are applying the J4J method or the 2D imaging speed. For which is need to have an imaging with a good level of the content. Using the best, we can simulate two scenarios for the range. Based we are the particle size 0.15 millimeters and heavy right with 3 millimeters. I made to the 2D and 3D reconstruction using different scanning methods to improve the general images. In 3D imaging test, for elemental testing, we use of the FRF or the 15 millimeter in the diameter. With a distance of the 20 centimeter, the focal length of the vision system. Due to effects scattering, we can see some imperfection over surface reconstruction. An example of the 3D reconstruction when missing data set applying power cross algorithms. For reconstruction, we apply unified reflectance model. For reconstruction 3D, we apply the method Economic plating and unified reflection model. This model is one combination of Lambert reflect model and of the Oren-Mayer model. We consider surface roughness of the objects. For solving a Conan equation, we apply Hamiltonian over unified reflection model. Effective schematic, effective geometric, of the local survive point is the unity normal of the survive point, and respective angle are the camera, direction by, and incident light direction L. Respective L is reflection light direction H is the unit angular fixation B of the lamp. Sigma is the angle between a normal and H. Scanning method and scenario. Depending on the type scenario, we can apply different scanning methods: basic, viewer, zigzag, and spiral. Here we can see that the 2D and 3D reconstruction of the flat figures, the zigzag and viewer, I have the best performer. For the width can be adapted at the best and urban scenarios with the buildings. While that in the forest scenario, where the shades presents curves as a tree and rock, the field scanning is a recommended. Evaluation of the processing time. The evaluation of the processing time has arrived times between 129 to 170 milliseconds to the 3D image. With that, the research rate of around 6 frames per second is close to shows reports in the literature, which is around 10 frames per second. The best scanning is faster with a time of the 129 milliseconds. Near speed and new vision system for this. With the 5 parameter lines, near speed to integrate into UVS. We consider some parameter design, the blur and the exposure value EV. In condition on the right, EV is the less core. It has water correspond to fairly cloudy with an ISO speed by 2/3. In condition blue, it needs to have power ISO height. This parameter defines the sensitivity of our system to operate on the right condition. The ring operation is seen in is we consider on a scenario when the system integrates in the flight. We define the flying speed two different heights, right from the 7.5 to 20 meters per second. For a motion blue, below 20% based on parameter of the need estimate. Conclusion: in the condition of the fine business, we have the side droplets below 1 millimeter. The scattering effect is more sensitive, so the 3D reconstruction has limitations. In the running condition for 3D reconstruction, you need to define a robust unified reference model. In the entire scenario, we can adapt the scanning. For example, in urban ambient, we have many buildings. The 3D reconstruction is focused on detecting what zigzag and fiber scanning can adapt best. While for scenarios, the speed scanning is more recommended. The next speed represents a right measure between 22 to 30 centimeters. This can be increasing to right power height. The processing time to the 3D reconstruction is between 129 to 116 milliseconds, with heavy scanning and the faster. Integration near SPA in the rate is feasible by any further testing. Here is only present as a proof of concept. Question
Thank you
Any
very much.
question?
Yeah. While we wait for questions from the audience, I have a couple. So right now, the methods that you tested do not consider, I mean, they don't know the amount of drizzle or if it's a rainstorm or anything like that, right? I mean, they just, you are feeding the information to them as is without, and the methods don't have any knowledge of the type of rainfall that is occurring. Am I understanding that correctly?
Right. My test only center of the scenario of the test. This system is a proof concept because in that moment I now have a commercial single piece adapter. Now is concentration in the reconstruction images using low resolution because using infrared over a scenario. The infrared has advanced because work in dispersion scenario, different of the vision system. In that moment, the type processing is below 200 milliseconds to reconstruction 3D image.
Go ahead. Right. So the reason why I'm asking that is because I'm wondering if it will be possible. I mean, it may be possible to feed onto, I'm not saying to these models or to these methods specifically, but to create a method that uses the information of saying there is rainfall or there is a fine drizzle. I mean, to feed that method or whatever method that you think that we can build or that you can build, to feed onto that not only the information from the from this PI, but also from the information that this is the type of weather that you are experiencing right now, and thus use that as a way to counter or maybe even feed that onto the reflective model. Do you see that happening? And if so, what do you believe that there will be, if there will be a next step towards that direction of using the weather model as part of your reconstruction?
Okay, in future, I will add to my method, the construction for adapter of the condition of the scenario, the illumination. In that moment, I test using develop one method using different scanning modems. Okay, this scanning method is adapter of the condition of the illumination and the scenario the test. In that moment.
Right. Okay. Well, thank you very much. I'm not seeing many other questions from the audience, and considering that right after this we have the award ceremony, I'm going to call the session over right now so that we have some time to prepare. So thank you very much for all the presenters. And Jose, this is